Good afternoon, ladies and gentlemen. It's a pleasure to see you in such large quantities here. And it's a pleasure for me to share some of the insights of the study I performed for NVMP with you this afternoon. Let me take you a bit back to where this research started. André Habert and I were walking some time ago at one of the recycling plants and just walking in between the scrap and the sorted fractions and the products lying around there. And André said to me, wouldn't it be good, after looking at how much of the critical and other materials are present in the end-of-life waste or products we collect today, to look more in detail into the relation between design and recycling and see what NVMP, together with your expertise, can say about bringing together these two different worlds and see if we can come up with a practical and realistic approach to design for recycling in which all stakeholders are presented and represented. That was a very exciting challenge, and that also coincided very much with my own background and research over the last 15 years in the work of, in the field of recycling and design for recycling. And my background is mining engineer, so I'm a minerals processing, a process engineer from background. And that background, and my colleague will also expand on that later on, as we've been working very closely together in this field. Professor Marcus Reuter, you heard him a moment ago. That expertise dates back for him already 30 years ago. So it's not just new business, but it's applying things we know about technology in the new field of resource efficiency and see how we can bring these two different worlds together. We've done that in the past for the automotive industry to look at design for recycling, and André already indicated, use easy to tear apart connections. You can imagine for cars, that's a bit of utopian, and you don't want that because you don't want to drive around your car falling apart. So what I'll try to do and share with you this afternoon in the next 50 minutes is show how can we bring together, like you see here in a bit of a graphical representation, the world of design and also the functional demands which are imposed on design and all the other reasons why we design and make products, together with the recycling industry and the expertise there. How can we use technology knowledge of both worlds and bring that together by looking in depth, and I will take you into the detail of materials, like André indicated, of quality of materials. How do you bring materials together in a product? Which materials do you bring together? How will they look like after sorting? How well can you do that? But also, what disappears still? And how can we change design? If we have the choice, how can we guide these choices in design in respect of all the demands around it? So let's keep it realistic. And also keep in mind that 100% recycling resource efficiency will never be reached because we always lose something. We mix materials in a complex way, and you see that here. We have an end-of-life product. We bring materials together. Chemical connections, very complex. So recycling is there to take it apart in as pure streams as possible. But sometimes that's not always possible. And you see that a bit in the colored bullets there up there. I don't have a pointer, but you see it. The yellow, the blue are all the metals we like to get out. But you see all the particles containing two or more materials because they are so closely attached. So how can we bring that knowledge of recycling, which you see in the first part, the dismantling, the shredding, the sorting, the physical treatment, which is very often regarded as just being recycling, but there's more to it because the materials are recovered in the metallurgical processing, the metallurgy. This is where all the nicely sorted fractions are recovered back as metals. What is in there? That determines what we can get back and how much. So how can we go through that chain? So how can we use the product as a resource? Knowing technology, knowing design. So how can we define, and then I come back to the question, initial question of André, can we come up with 10 rules? And I will indicate to you later what that means, the 10 geboden. I don't want to go that way, but I'd like to show you what that means and how we can use that to optimize resource efficiency. What is necessary? Which players are necessary to do that, and which tools? Because there is an answer. So let me start off positively. There's an answer and tools to do it. And go through these different steps. How can we collect streams, but mix them in the right way so that we have the right mix of materials together in a fraction to sort them optimally? How can we do this design for disassembly, but also for liberation, for shredding, for sorting, but also look in the end which materials remain together and we would like to get apart, and how is that playing a role in metallurgy? So design for metallurgy, for final treatment. Please, I'm just showing this to you. I've highlighted the major points, but I will take you step by step to each of these 10 rules. I start with the first 5 ones, which are in fact the basic fundamental rules. And I like to only highlight the first one. In spite of the fact that we have 10 rules here, also according to the wish of NVMP, and it's a nice way of showing how you can play around with that. But the basic rule, in fact, is it's impossible to define general rules because each product, due to its unique fingerprint of combined materials and metals, has its own recyclability profile, has its own recycling percentages, not only in general quantities, but also per material. And based on the way they're mixed, the answer is different. Based on the way you sort them, you shred them, if you use dismantling, yes or no, the answer is different. So what it's immediately saying is that we need knowledge, and the other rules automatically follow from that, that we need knowledge throughout the entire system on the technology, on the process, the materials, how we can design, how we can get our materials back. So you see the other way, simulation-based quantification. I will allude that to much more detail. Design data, infrastructures, technology, rigorous tools, CAD design linked to recycling knowledge, recycling simulation tools. In the end, the answer to do really design for recycling in practice with all the players involved. Based on these 5 fundamental rules, we came up with 5 additional rules, the more practical ones. But this could be extended to a much more longer list, which are specific for each product and different for each product. Looking at materials, material incompatibility, how can we design taking all the technology into consideration? I will show you some very clear and practical examples, also based on the input from the recyclers for that. And liberation. So please allow me to take you to the first 5, the basic rules, where we laid down the basic principles and technology, the knowledge for deriving any design rule. But keep in mind, the answers need to be arrived for a product separately because they are all different. Let me take the step back to where I come from, and that's mining, minerals processing. And if we have an ore, and you see that on the left-hand side, it's a mixture of different materials. And the metallurgical industry, the processing industry, is very much tuned to recover as much materials as possible from that ore. The copper ore doesn't only contain copper, but also iron, sulfides, name it. We know what's in there. But now we have our products as a resource. So not the ore from a mine, which is more or less, depending on the mine, stable. But we have different products with all the different compositions. And depending on how that product looks like, how the materials are brought together, so the product design, the material combinations, we create a new mineral, the artificial product mineral, which is much more complex and much more challenging than the mineral ore from which we mine from the ground, from the earth. But also, if we go a bit more to depth, we see also when we go through the product and open it and look really into detail in it, we see the printed wireboard, for example, with all different materials brought together. But the one printed wireboard is also different from the other one. What materials are present on that board? Are there other materials? Is there an aluminum heatsink? Are there steel-containing power supply parts? Or are they in a different one? What is in the electronic components? Which chemical compounds? And André already mentioned tantalum, which is used in the capacitors. but also together with other materials. So how do we deal with that? This is the mineralogy we've created. This also illustrates that every product is different and why recycling profile is different. So the first rule. And what you see in the last picture, and I took that from the fractions I received from the recyclers cooperating to this research, is a particle, aluminum. But you see here, and of course I picked out the not nice one to show you what can happen and what is reality in recycling, that it contains more material than just the aluminum we want. To quickly show you, and this comes from the previous research for NVMP, where we said, okay, we look at critical materials. I'm not going to guide you through the entire table, just as an example. Look at the platinum group metals, which has been pointed out by the European Commission as a critical material in the discussion on resource efficiency. And if I look at palladium in, for example, a mobile telephone, the concentration is so high, it goes into the nice metallurgical furnaces, the right direction to get it back. But then we come to the next one. We see, for example, the washing machine. And André also mentioned that example. The printed wire board on which the palladium is present is very small, in very small quantity within that entire large product. And the gold content, the palladium content is very low in comparison to the palladium content in that mobile telephone or a computer or name it. Also, due to the weight-based recycling legislation we have, there's a focus on getting back as much material as possible. So the printed wire board disappears. It's threaded, it might be sorted partially, but it might disappear. So then the recovery of the palladium is not such a logical issue. So that's different. You see that also for the other large household appliances and for the other materials. But just to give you a feeling why design for recycling is also product specific, but also depending on the processing route you follow. For example, the tantalum. Can I take out the capacitor, yes or no? And what do I do with it? Do I have sorting technology available to recover it as a tantalum capacitor, or does it disperse throughout the system because it's so small? Determines if I can recover it, yes or no. So also recycling route is determining. The other part of the first rule is that we don't want oversimplification. Maybe a bit a busy figure, but just to show you what resource efficiency is about, what recycling is about, and what design and recycling system is about. You see here all the different steps from the product created with all the materials, but all the other obligations taken in mind. Getting the material back, the market, where does it remain? André mentioned it, so many tons, millions of tons of material present in the market. When do we get it back? What are the mixtures of that particular population we get back in a certain moment of time? What mixtures of products, of materials are in there? How do we recover? How do we dismantle? What can we dismantle? Think back of the example of washing machine versus the mobile telephone by getting materials out, just as to give a feeling. What do we lose? How do we thread, sort? Which processes do we operate? Losses are inevitable because we bring together materials so closely connected, and it's a fallacy to think that you never lose. In threading, you will always lose something. There will something drop off and go to the wrong fraction, not even taking into consideration that the particles are not pure and end up in the wrong way. So this is the entire picture. So if we speak about design for recycling, this is in fact the depth, the complexity, but also the possibilities we have available to solve that issue and to come up with real rules which do not block the designer in their process. If you say, okay, I cannot combine ferrous with non-ferrous metals, then the designer would say, okay, can I still design my product then? It's getting difficult. So rather look at the possibilities and say, okay, but if you have this product and so much material, then you can do this or that. And if you have the choice, avoid that. So much more specific, but allowing the creativity and the demands also for the designer, but also showing the possibilities of recycling technology. That brings me to my second basic rule, is quantification. if we have a product and we start threading it, and you see it if you walk around on the recycling plant, of course the recyclers know that, but maybe not all of you. And we want to divide or separate the product into nice, pure fractions, at least as far as possible. A ferrous fraction, a steel-containing fraction, aluminum, copper, plastic, maybe, depending on the product, also a printed wireboard fraction. And there are many others, just showing. But the moment we have these materials in and brought together, these fractions are never 100% pure. That's simply reality. And you see it there. Sorry, it's moving, but a ferrous fraction containing a printed circuit board particle, but also the printed circuit board recyclate fraction in the middle. A plastic recyclate, also particles ending up. A residue fraction, where the moment you start threading printed circuit boards, and Yumiko has also investigated in the past, how much do you lose because you tear off these small electronic components containing particularly the critical materials, and they disperse throughout the system and end up also partially in the residue. But you want to quantify how much is being lost. Is it 10%, 5, 1 ppm? The moment you know that, then you can start thinking about redesign. Where in my design do I find the reason for these losses, and how can I change that? And the moment I change design, what is the effect? Does it make sense to do it, yes or no? So quantification is a very important issue, to know what is going where, how pure are the streams, what is the reason for that, what is in the particles after liberation as a consequence of what I bring together in design. And just zoom in into the printed circuit board fraction. The answer is also not the same. The moment I dismantle, on your left side, it looks different than when I start threading. Is the printed circuit board fraction just containing the printed circuit board? Is there still a heatsink on? Yes or no? Where are the electronical components? Are they still present? How much is being lost? And how much metal loss does that imply? So over this entire system, which you see here, you want to quantify, need to quantify what is the effect of the products I collect. What is in the products? And we speak about urban mining. But we want to know, if we speak about urban mining and getting data on the urban mine, it's not enough to say so many tonnages. If we want to do design for recycling, we also want to know what is getting in, which products, which materials, what is there. So there's also detailed data demand to do it on the same level as you operate recycling technology. Did you want to know what is in your recyclates? What is disappearing where? What is being recovered there? So real hardcore values. So there's a need for simulation tools to calculate through the system and quantify how much do I recover, how much do I lose, where, and what is the reason for that. I will show that to you later on. And just keep in mind that these tools are used and my colleague Professor Reuter will also illustrate that or discuss that with you in much more detail, in industry to design multi-million-dollar plants, to simulate them, to set them up as part of the entire design process of a metallurgical plant. So it's real existing software used on that large scale to do that, which allows us also to do that on this level. That brings me to design data, and I mentioned it before, the third rule. The moment we dive into the system and want to get real answers on design for recycling and be able to pinpoint the issues, where do I have to change my design, and calculate and determine recycling rates not only on the generality of the product, but also on the critical material level, which are very often present as minor elements in the product, so in very low quantities. There's immediately that need of data. And from the work I do, I realized that that's also an enormous exercise and not always easy to get all that information. But I think we're also here together to look ahead and see where must we go to, which changes must we make, what information must we gather to do that. So that does mean that we cannot get away anymore with data on just so much steel, so much copper, so much aluminum, that's it. But go into the level. How is the product constructed? How is the structure of the product attached to the more complex components? Which materials are present in these complex components and in the electronic components? Which chemicals do we speak of? Because that mixture determines what we can back, where the materials are ending up. If my printed wire board goes to my printed wireboard fraction, or if there's a steel bolt attached to it, which is the reason that it goes to my steel fraction, because it's magnetic, it's picked up by the magnetic separator and goes the wrong way. Just an example on that. Brings me to the fourth rule. Of course, to do that, and I think that's clear from what I mentioned before, we need a good recycling and metallurgical infrastructure. So the technology needs to be in place and also maintained and safeguarded to make sure that we have the capability of getting the materials back. And if we speak about resource efficiency in Europe, in the Netherlands, but also in Europe, large technology is wider spread, so you can't have that in one country. That's also not necessary. So we also have to look over borders. It's important also for policy to realize that we have to safeguard our industry to make sure that we can keep the resources within at least European boundaries and be not too much dependent in the whole critical material issue on other countries, on technology. So we have that technology, we need that here. These are just some pictures. I got them from my colleague, Professor Reuter, and he will go into much more detail in what these processes do. So I'll leave it at here for that moment. That brings me once again to the tools. We need sophisticated tools which are able to capture all the complexities, the details of design, what we bring together, which processes are operated, and I very much realize, Andre was worried, that you can't read that. This is not the reason I'm showing that to you, but I will take you through it step by step later on at the end of my talk to show you what kind of answers you can get with these kind of tools. This is the process simulation tools, which is also used on large scale in industry. A product comes in, you have different processes, dismantling, shredding, sorting. You can look at the quality of the recyclates, how material elaborate, how much is recovered in the end in the metallurgical processing. That should give you a feeling at this moment. That brings me to the next 5 guidelines, and the last one I leave for the well-attending listener. I leave to close off with. So rule 5 you get in the end. Let's go to the simulated derived guidelines. So based on the fundamental principles, the technology principles, the physics of recycling technology, methodology, but also design, we can come up with much more practical rules, but always on that basis. As I mentioned in the beginning, various recyclers were also very kind to cooperate in this research, which was also very much appreciated, because in this exercise it's very important to bring the different industries together to make it a really industry exercise and come up with practical but also realistic answers for design for recycling. So some very specific and clear examples if we look through the products. And one of the guidelines is look at the material characteristics in sorting. How do they behave? Do you see problems in sorting? Are fractions being contaminated due to the use of certain materials? An example of that is the concrete in washing machines. And Hendrik and I and Bart and I have been at recyclers and at plants to dismantle also washing machines and different products. And I did it myself also for NVMP many times. I was glad then when I was pregnant that I still fitted in my overall to do it. So, but to take them out, to get a feeling, what is in these products? How are they attached? What is playing a role? And do they all look the same or are they different? And what materials are in there? And then you see that the concrete in the washing machine is attached in many different ways. So it's a disaster to get it out. It's very difficult, and that's also the feedback you get from the recyclers. It's very difficult to get it out. The moment you can't get it out, you start shredding, it dispersed over all different fractions. So that's an issue. Glass in fridges. Also feedback from the recyclers. At this moment it's regarded as process waste, so it's a direct loss in the recycling process. So it decreases the recycling performance. Isolation materials, especially in large household appliances, like washing machines or dishwashers. It's very fluffy material, It attaches to everything, the copper wire, so it ends up everywhere. And it's very difficult to get it back, but it's also contaminating the other fractions. Colored printed wired boards. The moment you look at your computer or mobile telephone and a bit closer, maybe open it. Some of them you can't open, but take a look at it. And sometimes you can see the color of the printed wire board. And where the printed wire board used to be green or brown, it's now being blue or red or purple. And that's an issue for the recyclers. The moment they use color-based sorting to remove the printed circuit board parts from the fraction, and it's based on brown and green, only the brown and green is removed. When the colors change, they either lose the other colors, or if they also add that to their system, they also get the other colored materials with it, so the different colored plastics. So either you lose printed wire boards, or you have a contaminated fraction of printed wire boards because you have much more plastics in it. So some very practical examples on a very clear design for recycling. Look at material characteristics, but this also says it's different for different products. Then I make the step to metallurgy, the incompatibility or compatibility of combined materials. And to many people, the example of copper and steel is very clear. If I make a steel fraction, a steel recyclate, I have to be careful not to insert too much copper, to have too much copper present in it, because it decreases the quality of the steel. So you see the example of one of my dismantling sessions here of an electromotor. I'm not saying that this is easy to solve, but it's important to know where it is. Another more complex one is the printed circuit boards, and I mentioned that before. What is on that board? Which other materials are there? What do the particles like after shredding? How pure are they? Which materials are on there? What is in my electronic components, in my capacitors, in my tantalum capacitors? Which other materials do come along? And can I get, from these combined materials, can I get the materials back, yes or no? If you remember the picture I showed in the beginning, on the different recyclate fraction, the iron fraction with the printed wire board. Do I get my gold and my palladium back there? Yes or no? That's what we need to know. So allow me to take you a bit through the metallurgy, very, very briefly. And Marcus will do that in much more detail. So what you see here is a graphical representation to give you a bit of a flavor of what metallurgy can and cannot do and how it's working. So if we look at, and I said that in the beginning, my background is mining, and also the basis of recycling lies back in the processing of minerals, also the technology we have available. So the metallurgical infrastructure we have around is based on primary metals. And what you see here is the primary carrier, the commodity metals. So we have a steel recycling infrastructure, a copper recycling infrastructure, an aluminum recycling infrastructure. So these are the blue, the metals in the blue circle in the middle, just to show you, give you a bit of a feeling what it's meaning. If we then take an example of a furnace, this is another tech furnace, just very roughly, we make a metal. You see that in the bottom. The light blue circle is representing the metal. I'm going to show you later on where the different metals which come together in a fraction will end up. The white one is the slag, the dust, the slime, the flue dust we produce, from which we still can get back most of the materials because it goes through another processing route. And the green one are the low value products. The materials ending up there will in fact be lost. So let me take the example of the printed circuit board and see what material combinations mean in respect to metallurgical processing and recovery or losing materials in that processing chain. You can't read it all. I picked out some: copper, iron, aluminum, gold, silver, palladium, platinum, but also tantalum and the rare earths, the zeldzame aardmetalen, which is also a favorite topic in many of the resource efficiency discussions. So if I now take the wheel and I take out the copper processing segment, and that is what, for example, Umicore is doing, what Bolide is doing, Dowa is doing, so there are many different processing plants, taking up the copper scrap, but also the printed wire board scrap to recover the materials from it. If I then look at the copper, of course, it's recovered. But also a small percentage might end up as a loss because it oxidizes. It makes a combination with oxygen. So that immediately tells us recycling is also not only about do's and don'ts, yes or no, but also about how much. If I then take the iron and the aluminum, they react with oxygen, they go into the slag, they get lost. They also affect the process operation, the recovery. It might affect also the recovery of the copper. Marcus will discuss that. I'll leave it at that for the moment. But the nice platinum group metals, gold, silver, palladium, platinum, they're very well recovered in these type of processes. So the moment the printed wire board goes into that direction, no issue. Although it's combined with copper, with iron, with aluminum, it's no problem. But if we look at tantalum, that's one. And the rare earths are very stable as an oxide, and they will go lost. So the green is saying you can recover it. The yellow is saying, okay, we make a slag in the process, we use aluminum for that, we use silicon, so we lose it anyhow, we use it anyhow, and the reds are really lost. So the moment we speak about rare earths on a printed wire board, in these type of processes, it goes lost, because the concentration is so low that we cannot recover it in the processes anymore after smelting. The same applies for tantalum. So this also gives a feeling about redesign. Which materials can I combine together? Where do they go? Which processing route? And what happens then? Do I get them back, yes or no? Then I filled it in for you. I know you can't read it, but just to give you a feeling for all the different elements which might be present on a printed wire board. But it gives a very quick indicative feeling of the colors, which ones you can recover and which ones not. This is something to keep in mind in design for recycling. So that brings me to a kind of compatibility table, which you could use as a first screening tool to get a first feeling, where are the problems lying? Which materials do I lose the moment a printed wire board is going to my copper infrastructure? But the same applies, of course, for the moment my printed wire board or my copper is going to my steel plant or to my aluminum fraction. André say, okay, an aluminum particle attached to other materials. What is happening to these other materials? If I have aluminum in a product, it could be as a structural part, but it could also be present in a capacitor. The answer is different, because in the capacitor, different materials are attached to the aluminum. Do I get it back, yes or no? Does it go to the aluminum fraction, or does it go the other way around? Is there a steel bolt in it? Does it go along with the steel? Where does it end up? This is what this is showing. My steel infrastructure, so my steel recyclate I produce going to a steel smelter, to say it so blatantly. Copper is being lost because it's very noble. It's much more noble than the steel and it remains in the steel. Aluminum is very reactive with oxygen, so it goes to the slag. It's added anyhow in the process, but you lose the aluminum. From an energy perspective, aluminum is very energy intensive to produce from a primary source. You don't want that, or at least you want to know that's happening. But the moment you go to the copper smelter, I recover it. To my zinc lead smelter, you recover it. The same we can do for aluminum. What happens to aluminum going to steel? To the copper plant. You saw it already in the picture I indicated before. And then also the materials of particular interest in this discussion, the critical materials. And I took here the example of palladium and antimony. And you see, depending on which recyclate fraction it's going to. So how do I thread? How do I sort? Where is what going? The moment these materials go to my steel plant, I lose them. To my aluminum plant, I lose them because they nicely dissolve in the aluminum. But to go to the copper smelter, at least I can remove the palladium. So this is a kind of indicative tool, but still not giving quantities. That's why I also emphasize you need good tools to calculate also this. And then you can set up a nice compatibility table and put it next to your design and at least get a feeling of where are the problems lying. But then you should put it next to how do I thread, where is what going, how do my recyclates look like. So that brings me to the 8th rule, with that in mind, with the metallurgical process in mind. If I start designing, I can say, okay, I have a product, but can I design with this knowledge in mind? And look at this metal wheel, so to say it, or the compatibility tables, and say, okay, if I design a component in a product and I want to get out certain materials, based on this knowledge, I can look at the wheel and see, okay, which ones do I get back? These I can bring together, but then also I must make sure that they go the right direction when I start my sorting procedure and when I create my recycled fractions, to make sure that is it going this one? Once again, the example on the printed circuit board. I mean, there are many other ones, but just to guide you through on the same basis. There's aluminum in the heat sink on it. Will it go to the aluminum process? Then you have this picture where many of the materials are being lost, or will it go to the copper fraction? So this is the trade-off you need to have in mind when designing for recycling. So when I design, I say, okay, and I want to let it go to the copper fraction. These are the mix of metals it can deal with, and this is what I'll have to avoid. So that brings me immediately to the example of the tantalum capacitors. It's being lost, it's connected on the printed circuit board very often. When it goes along with the printed circuit board, it's being lost. It was a red bullet. So if we speak about design for recycling and think of how we can change design to improve the recovery of the materials, we need to think of options to label, for example, certain components or parts. But if we're to recognize them during sorting, but also in addition sorting technology to get them out of the stream and get them as a separate fraction. Another issue is then more on product level is the lamps, the glass in the lamps, which have to be, is different for different types of lamps. If we look at the compact fluorescent lamp versus the LED lamp, in fact, and that's also the feedback from the recyclers, you want them to sort them at the beginning to avoid mixing of the different glass types, the different materials in that lamp. Can you develop sorting technology or a kind of labeling or in the identification to recognize them beforehand to make sure that you can design for waste stream sorting? Another one is on the compressors of the cooling devices. And that's also very practical feedback from one of the recyclers. The mapping of a tapping point to make sure that when you connect and remove the liquids from the compressor, that you can empty it totally. But also the labeling in the cooling device at the fridges, which cooling liquid is being used. Put it on the same place, because the moment it's not visible which one it is, it's treated as the most dangerous one with all the cost affected to it. Also, which gas is used in the fluid system, but also in the foam, because that also might be different. So that's design for recycling, but also labeling on a very practical level and on very different levels. So it brings me to the last one, design for liberation. And iron steel bolts are, you hear that from every recycler as well, are an issue in recycling because they're magnetic and they do not always liberate nicely from the material. They are there to keep the materials together, and they do not always nicely liberate from each other. So here you see different examples, part of printed wireboard, plastic. Thinking of the metal wheel, we know what happens, what we lose, but these issues affect that. So can we avoid it? Can we redesign that it breaks apart at certain parts to avoid materials being dragged along to the wrong recycling stream? But also very other examples, not just on a steel board. I know CRT is fading out, but this was also one of the comments of the recyclers, the glass glued to the metal frame of the CRT. Shrink films, colored shrink films around the tubes, glued plastic and wood in large household appliances. It's very difficult to liberate that. These materials are not compatible. You cannot, the moment you have them together, you cannot recover them both. So you want them apart, but the moment they're glued together, that's very difficult to get them apart. Sealed batteries with the complex composition behind it, difficult to get it out. Polyurethane foam in fridges, in cooling devices, glued to the steel, to the aluminum, to the plastic. The moment the thread and the polyurethane foam is processed very nicely to remove all the cooling gas from it. But the moment it's going into another fraction, part of that is also being dragged along. And just to end off my rules with these very practical pictures of particles are found in recyclates on plants, on name it, of issues in design for liberation. And here you see what recycling is about and what design is about and which material and a range of material combinations you will find together the moment you start recycling products. And attached to each other, then they must be compatible to recover, and otherwise we must try to find a solution in design. But you need to go down to this level to be able to trace the losses and to be able to find an answer in design, where possible, of course. I mentioned in the beginning, and I'd like to use the last 5 to 10 minutes to show you a simulation example of the design for recycling tool. I quickly switch to that. This is what you see here, and I know it's a lot of information on one slide, but what you see here is the entire recycling flow sheet of a product. It's an example on small household appliances. Of course, for confidentiality reasons, the figures are indicative, but just to give you a feeling what kind of answers you can get out of such a tool and how you can use such a tool to quantify critical issues and to pinpoint critical issues in recycling, but also in design and in design for recycling to focus your design issues. Not to go through a standard list of rules which just block you in the design process, but really pinpoint for this product, it's this, that product, that, and we can, if we change it, we can improve it with that percentage. So what you see here is that we can calculate for the different processes how much material is coming out. So we can set up a mass balance. But we can also, if I click, and that's you see on the right-hand side, I cannot decrease that, but trust me if I say that you have a compositional balance of all materials which were in that product ending up in that specific fraction. So you know exactly what material is going where, in what quantities, how much is ending up, for example, together with the steel. How much steel, how many other elements, and what is happening with that. Also, after my furnaces, after my final treatment. So from the product, and I will go to the larger picture back, I can calculate how much copper do I make, how much slag, how much dust, how much steel, but also how much primary metals I have to add to dilute it to the right quality. In the end, what we all want to know is recycling rates. And that's not just a general one, but also for the different metals. Here I took the aluminum as an example, the copper, the iron, the tantalum, palladium. This is for a specific scenario. So what it shows is that for all, and this is just an example, I didn't want to list everything, but for all the materials, all the elements in a product, you can calculate recycling rates. Just go back to the overview to show you what more you can see. So it's showing composition, dismantling, metallurgy, but also a recycling rate, a recyclability index, which is so detailed that you can also show the effect of the effort a designer, an OEM, has done in his design process to improve recyclability. If you can't go to the level of recycling rates per material and the detail which is affecting that, you cannot show the effort the OEMs has done to do that. This is on a general level. What is also nice to see, for example, if we speak about the critical materials, and I take here the example of gold, and you see it on the thickness of the lines, is how much material, how much gold is going where? Where is my gold going? And you see it, the large fraction going to the printed circuit board fraction, going different ways. But you see for all fractions, you can know where is that element going, and you can do that for all the elements. Just to give you a feeling, what is the quality of my streams, for example, after sorting, but also after processing. So what do I produce in the end from it, and how much material do I get back? So how can we use this for redesign options? And I've now taken another example on the basis of the one you showed before, I showed to you before, is if we redesign, if we improve the removal or the sorting of printed circuit boards or of tantalum capacitors through design changes, either by labeling or identification options, what does the picture look like now? Maybe it's very difficult for you to read, but the recycling rates are marked in red. Tantalum is going from 0% to around 80%, but not 100, because there are other materials attached to it. And like I said, it's indicative, but just to give you a feeling, how does it change? My palladium increases from around 45 to almost 80% because I remove my capacitor and put it into the right direction. But my elements going along with it, like steel and copper, might decrease because they go into a process, the copper furnace, where they are not recovered. So it's always an interplay between different materials, what goes where. So this is how these tools like and which answers you can get from it to really connect design and what you change in design to recycling. Here's the example of the gold distribution. You see at the moment you start dismantling the gold, the thick lines are moving and is going to a different fraction, being recovered. Design for liberation, if we look at the printed circuit board once again, and we say, okay, we design it in such a way that my aluminum heat sinks can be removed, or my iron-containing parts, or my iron-containing balls are being removed, then my sorting is improved. More printed circuit boards are not going along with the steel fraction, but in the right direction with a much purer quality, leading to a higher recycling rate of both aluminum and copper, but also of the PGMs, for example. So you can make that very clear, visible, and really put hard figures to that. The moment you make a change, it's also visualized. So that brings me to my two last slides, and I'd like to end off with looking ahead. So what I'd like to share with you is what is the detail and knowledge and basic ideas behind design for recycling? What are the actual facts and technology playing a role? What must we look at? And that design for recycling is not product specific, but each product has a different profile. But with these tools, which are used in industry on large scale, good design data, bringing together these different worlds, putting the experts around the table and using tools like this, design for recycling is possible. We can quantify, we can pinpoint, get figures, know where we have to design, and also even link it to environmental analysis, because we have a good mass balance. We do not only know what we recover, but also what we lose. What is in our fractions, which, for example, dispose of to landfill? Are there hazardous materials present, yes or no? And that's a different picture than a general environmental analysis where I say aluminum, so much percent, iron, so much percent. It's so different per product. So we can calculate, quantify it, and also get figures, get indication for design within these tools, within bringing these worlds together, and even bring it together with environmental analysis also to include that. So that's a very positive look ahead. It's complex. You need to have knowledge on what is happening, but a designer has knowledge on what he does. A recycler has knowledge on what he or she does. So on the entire system, we have to bring together this knowledge, and it's possible to do that. So I hope this conference and this study, and also all the people together here, is also a step ahead into that direction, that we can make it happen, and at least make a first step to start with that. So that brings me by my recommendation, as policy recommendation, that if you think about policy recommendations about recycling or eco-design, but also in the discussion about recycling and eco-design or design for recycling, you should remain what is technologically possible, physically, chemically, but also economically, of course. We have to run a plant. It has to be economical, feasible to do that. We must know that 100% is never possible. We must realize that when we set up targets. And how far we can get is determined by technology, by economics, by bringing together functional demands of design together with recycling technology. But you also should stimulate best available recycling infrastructures, and that's also what you hear from the recyclers. We also want to distinguish ourselves. It's good that we have a system like NVMP where we have to report what we do, because it's also a way that we can show how good we are in what we're doing. But if you also set up legislation, also give room for best available technology, techniques, and improve that or stimulate that on recycling and metallurgical field both. And in the end, you should bring together the expertise of all stakeholders in the system in order to make it happen. And I hope that's a way to do it, not only today, but also looking ahead. And in that sense, we also need to take into consideration the products of today, what we get back as end-of-life products now, but also what we will be designing in future. So that means also an exercise which I hope we can start all together, and thanks to NVMP taking this initiative, that we can do that and bring the different people together, and it's possible to do it. We have the tools and we have the knowledge. So thank you very much for your kind attention.